Okay, this is the Spandex Fabric of Space-Time video for the lab. This lab demonstrates the effects of gravity and a good introduction to the gravity units. So this spandex cloth stretched across the frame here represents space and time. The model gives us a length, width, and depth, so 3 dimensions. In reality, we have length, width, depth, and time as the 4th dimension. Einstein, in his theory of relativity, combined gravity and time and relates the two, which we're not really going to get into at this lab, but do realize that that is the 4th dimension, is gravity and time. But our model only has the two, and the sagging or bowing of the spandex represents the distortions of gravity. So, if we roll a marble across this fabric of space, okay, it should travel in a straight line. Because Newton's first law of motion is an object in motion will stay in motion unless acted upon by an outside force. Now, obviously, when the marble rolls to the side, it's going to bounce off the edge and come back. But if this was space, there is no friction or air resistance in space to slow it down. So it should travel in a straight line forever until it gets some interaction from another force. Like another marble. So if we roll 2 marbles across, you'll see that their paths are no longer straight lines, but that they interact. And that their paths are curved until they collide. We'll do that again so you can see that. So they bend towards each other and no longer are their paths straight. They come together and combine. And this works if both marbles are moving or if one is stationary in the center. So as long as it stays there centered, if I roll another marble towards it, they will interact. It'll turn the path of the moving marble and eventually bend it towards the one that's not moving, and it will be attracted to it as well. So they kind of do a little spiral dance there at the bottom. They're interacting because gravity is always an attractive force. So any object that is mass is going to have gravity, and it will be attracted to any other objects that have mass and gravity. So now we're going to place masses of different weight onto the model and show how different masses cause gravity of different amounts. So if we put a small mass on the spandex, it warps space-time a little bit. But if we put a larger mass at the center, it warps quite a bit more. This is because gravity is directly related to mass. The more mass an object has, the more it's going to distort the space-time and the more gravity it's going to have. So a larger mass, it's going to warp space-time more, causing more gravity. Now, if this is a model of our solar system, the object in the center, the mass in the center, represents the sun. All the objects in our solar system revolve around the sun. So if I place a marble on the edge and let go of it, it should roll in a straight line straight to the mass in the center because of that attractive force of gravity. But if I roll a marble a little bit off to the side, try that again, a little bit off to the side, try it again, the path is not straight, it curves. Now eventually it comes back. It'll curve outward, come back, and then roll back in, falling into an orbit that eventually decays and hits the center. But if I give it enough force or velocity, it'll get shot right out of the solar system. Okay, and then we call that speed at which you can escape the gravity of another object, escape velocity. So the speed at which you need to be traveling to escape the pull of gravity is what we call escape velocity. And then for most things like Earth, we talk about using a rocket to escape Earth's gravity. We just have to reach enough to overcome Earth's gravity. In the case of a black hole, nothing can go fast enough to escape a black hole, not even light, the fastest thing in the universe. So that's why a black hole is black. Nothing can escape, not even light. Okay, we're going to switch out the large mass for the small mass. And I want you to look at how the marble rolls toward the small mass. Okay, as it gets closer, it does speed up. Gravity is an accelerative force. So as it gets close to the object, it will go faster. But if we compare the speed of these marbles, their final speed, their final acceleration, to that of the larger mass, we'll find that the marbles will get more speed faster. They'll accelerate more going toward this larger mass. So here on Earth, everything is attracted to Earth with an accelerated force of 9.8 meters per second squared. And they will always be pulled towards the Earth at that speed. So changing the mass at the center will affect the accelerated force of gravity. The larger the mass, the more the acceleration of gravity will be. So force and gravity, mass and the force of gravity are directly related. As mass goes up, so does the gravitational force. If we give a marble a little bit of an orbit, we'll see that the marble travels faster as it gets closer. This is because as it gets closer, the space-time is warped more and the effect of gravity is stronger. So as distance gets smaller, gravity goes up. This is an inverse relationship. It's an indirect or inverse relationship. So what's weird is if we do two marbles of different mass let go at the same place, even though we know that mass is directly related to the force of gravity, the largest mass is so much more massive than these two small masses that they should hit at the same time, or very, very close. And we know that all objects on Earth fall at an accelerated rate of 9.8 meters per second squared and should hit the ground if there was no change in the air resistance. This is because the masses of the falling objects are so much smaller than Earth that there is no change. Go ahead and stop it. Okay, so an orbit is the shape of an object's path as it revolves around something. So the Earth goes around an orbit around the sun, and if we give the marbles a little bit of sideways velocity, they do this really weird elongated oval. Whoops. This elongated oval, which we call an ellipse. As the marble moves around in its orbit, you'll see that it moves fastest where it's closest to the mass, and then it gets slungshot out, and gets slower the farther away it is, and then turns around and comes back, and gets this really weird elliptical shape. However, if we give the marbles a little bit more sideways motion, the orbit becomes more circular. Earth's orbit is very, very close to a circle, although there is times when the Earth is closer to the sun and times when it's further from the sun. The average distance the Earth is from the sun never changes. Now, the closeness of the Earth to the sun is not much of a change between its closest and farthest place. And the climate on Earth is not related to that distance. If it were, then both the northern and southern hemispheres would experience the same seasons, but we know they're reversed. When it's summer in the north, it's winter in the south. When it's winter in the north, it's summer in the south. And that's because of the tilt of the Earth, not its orbit. But our orbit doesn't decay, it doesn't get smaller, like these, which as they go around, get smaller and smaller. That is because our model has a key problem that doesn't exist out in space, and that is friction. As the marbles move around the mass, they're interacting with the spandex. And even though this is slick and the marbles are slick glass, there's enough friction to slow them down. That slowing of their velocity makes them spiral down to the center. And eventually they'll crash into the sun. But that doesn't happen out in space. There's no air resistance, there's no friction slowing down the Earth as it revolves around the sun. So we will keep going around the sun as long as none of the other planets' orbits change and our orbit isn't affected by another object's gravity. We'll keep going probably until the sun explodes and we all die. Okay. Now, if we introduce a large marble and a small marble together, it will simulate a really interesting thing that actually does happen in our solar system. Get them going together. So you see the little marble follows the large marble, just like the moon revolves around the Earth. Okay, the little marble acts like a satellite, a moon, of the large marble, until it gets close enough to the sun that the sun's gravity interacts and throws that moon off of it. And this is actually why Mercury and Venus don't have moons, but we do. We have our moon, Luna. The Martian system, Mars, has 2 moons, Phobos and Deimos. Okay? And then past it, there is the asteroid field, and then Jupiter, which is incredibly larger than Earth, and it is massive enough that it has hundreds of moons. So we can do a lot of moons, and you can see that they all kind of stick together with the larger planet until they get close to the sun. So that models planetary systems with moons. Go ahead and stop it so that we get messed up again. Did you stop it? All right, so we've looked at a moon and planet system. Now we're going to model the solar system. So we're going to add several marbles going all at once to model the solar system. Okay, now, of course, in our real solar system, the sun doesn't pull things towards it. Again, we've got friction that's slowing our marbles down. But as they get closer to the sun, they go faster. That's because as you get closer to the source of gravity, the force is stronger, so you've got to be moving faster to stay in orbit. And of course, the ones that are really far away go slower, not only because they have a longer distance to travel, but they're moving at a slower velocity. So planets like Neptune and the dwarf planet Pluto, quite a ways away from the sun, have a much larger orbit and take a lot longer to go around the sun than we do. Of course, our orbit is 1 year, whereas planets beyond our orbit will be longer than a year, measured by our time. So, if we introduce marbles into our solar system of different masses, sometimes those large masses can catch the smaller masses and create moon systems as they go around. So if I can get this going, several. Okay, so the big mass, the big planets, will sometimes grab smaller planets, or smaller planets will bunch up and create systems with moons. The little steel ball bearings are a little bit heavier, so they'll gather up moons. So when a large mass object comes into the solar system, it can actually kind of sweep up all the mess, and that's actually what Jupiter does. Jupiter flies around its orbit, and any stray comet, any stray asteroid, it usually gets swept up by Jupiter's orbit. If we didn't have Jupiter in our solar system, the likelihood that Earth would be hit by an asteroid would increase quite a bit. Okay, so if we this time introduce marbles going opposite directions, so some will be going one way, The others would go in the other way. Okay, it stands to reason that some of them might collide. Okay, they'll cancel each other out because they are trying to compete for the same space. So they wind up getting moved into each other and collide and cancel each other out. This is very, very similar to the way that the solar system formed at the very beginning. When, right after the sun formed, our solar system was just a massive cloud of gas and dust. Okay? And we basically had everything going random. And what happened is that after everything cancels out, there's a preferred motion of what's left. And that's actually what happened in our solar system. All of the planets that were left over wound up going in the same direction. All of our planets go counterclockwise. So if we have all the marbles in the center, this represents a large mass. I'm going to push down on it and get the marbles to start following me. Now what's really cool is you get it going, they'll sling out into this spiral arm shape. And that's actually the same shape that our galaxy is in. It's a spiral arm. At the center of our galaxy is a supermassive black hole. So just like our moon orbits us, and we orbit the sun orbits a supermassive black hole at the center of the galaxy. Now, galaxies can even orbit other galaxies. We actually have a small satellite galaxy called Triangulum, which orbits the galaxy Andromeda, which is moving toward us and may actually intersect with us. Now, black holes don't actually go around the universe swallowing everything up, but they are big and powerful sources of gravity. But if you're going fast enough, you can actually move around and orbit a black hole. You just don't want to get too close so that you're going too slow to overcome its gravitational pull. Remember, we talked about escape velocity. You have to be going fast enough to escape the pull of whatever object's gravity is, and a black hole, by definition, has so much gravity that not even light, the fastest thing in the universe, can escape.